So, today what we're going to be talking about is a little bit more about limit stuff, and in particular, I want to take a look at infinite limits and limits at infinity. These are two situations that are similar to the kind of limits we learned about last week. However, there are some differences. Let's begin with infinite limits. Now, the thing about infinite limits is this. There's a few different ways that a function can fail to have a limit. Okay, so for example, if I have something like, let me just draw a few examples. I could fail to have a limit because maybe at a given point, I don't have the same limit on the left as on the right. So in this case, my function does this jumping business. I do have a well-defined left and right-hand limit. There are some specific numbers here, but they're not the same, therefore I don't have a limit. Another thing that I could do is I could have that thing like we had with sine of 1 over x. So I could have something that just starts shaking around an infinite amount and doesn't approach any one particular value. So that would be another way I could fail to have a limit. But a third way that I could fail to have a limit is maybe I've got something like this, where I have a vertical asymptote. And if I have a vertical asymptote like that, well, that's kind of a different matter than what we have in these other cases. And so we consider a situation like this to be an infinite limit. If at a given point, if the function gets arbitrarily large, we will consider that an infinite limit. We would also consider it to be an infinite limit if we had a vertical asymptote and on both sides the function goes down towards negative infinity. So in this case, if this is x equals a and this is x equals b, and this is my function y equals f of x, what we want to say is that the limit as x approaches a of f of x is equal to infinity, and the limit as x approaches b of f of x is equal to negative infinity. Interestingly, well, that's not going to work. My light has gone out. Give me a few moments to deal with this. All right, sorry about that. There was a minor problem with the fuse box, which has now been fixed. Moving back to what we were talking about. One thing I want you to keep in mind. Strictly speaking, these are cases where the limits do not exist as real numbers. So in one sense, if I asked you what is the limit as f of x approaches a, you could say, well, it's not a number. It doesn't exist as a number. However, it does have interesting behavior near a, and we want to capture that by saying, well, the limit is, it blows up to infinity. That's what the function is doing there. Yeah, it doesn't have a number as a limit, but it does blow up to infinity, and so in that sense, we can kind of say, we write it with the same notation. So it's a little bit confusing, I think, and that's why I'm kind of harping on this and trying to emphasize the difference. I'm not literally saying, this isn't a real number. Infinity is not a point on the real number line. Therefore, you cannot say this is equal to infinity as a number. But what you can do is you can say, we will interpret this to mean this thing blows up to infinity. It infinitely blows up. And similarly, negative infinity. That is not a real number. It's not one of the real numbers. What this means is this thing blows up, but it goes downward. It's still blowing up, but it's in the downward direction that it's blowing up. Okay, that sounds confusing in English. I blame the English language. It's not the math's fault this time that is confusing. So that is what we mean when we talk about infinite limits. And similarly, we can have one-sided infinite limits. So in a situation like this, let's say this is my x equals a line. If I have this kind of thing going on where it blows up in different directions on either side, well, in this case, I would say, and let's say this is my y equals g of x, the limit as x approaches a from the left of g of x, this will be equal, I drew the wrong thing. I'm being kind of ridiculous here because perhaps the fuse box has still got me thrown. So I wanted to draw it this way. As we come in from the left, this is blowing up towards positive infinity. But as we come in from the right-hand side, this is going down towards negative infinity. So you can see here that there is this kind of different behavior. Now, how do we actually make this precise? I think it's not usually, it's not so bad maybe to see what's going on here on a graph. But if we want to actually see what's going on in terms of a precise definition, how can we do that? Well, it's not actually too difficult to do if we think back to our epsilon delta definition, but we do kind of need to be careful about it because it's no longer like we can say, oh, we can get within epsilon of our target, right? Normally when we think of a limit, we're trying to force the function to be within some small number epsilon of our limit. But that's not going to work anymore because infinity isn't a number, negative infinity isn't a number. So here's what we are going to say. The limit as x approaches a of f of x is equal to infinity, or respectively negative infinity, if for any n there is a delta bigger than 0 such that when 0 is less than absolute value of x minus a is less than delta, f of x is bigger than n, or respectively, f of x is smaller than n. Now, let's think through what this really means, because like the epsilon delta definition, I think this sounds a little confusing, but it kind of sounds more confusing when you read it this way than it is when you think about what this is really saying. What is this really saying? It's saying that n here is keeping track of how big do we want the function to be. We want to make sure that the function is at least, it's bigger than n. Well, we can force the function to be bigger than n by just requiring it to be within delta of n. But we can do that no matter how big you make n. In other words, on the graph, I can guarantee that I'm going to be above this line y equals n by just restricting myself to some interval of width delta around a. As long as I am within that, my function is going to be above this minimum line of n. But because I can do that for any n, that's saying that the function must be blowing up around a, because I can guarantee that we hit as large as you want just by making that delta sufficiently small. Same deal for the negative infinity case, except in this case, we're saying that we can do the same picture but upside down. So I'm not going to redraw the whole thing, but think about if I can make this n a very large negative number and guarantee that my function is below that large negative number by just ensuring that I'm close to a. Close to a meaning within delta of a. So it's kind of like the epsilon delta thing, okay? The epsilon delta thing is a very confusing statement. If you just sort of read it, you're like, what is going on here? But if you kind of break down what each of the pieces is saying, each of the pieces just encapsulate what we are intuitively thinking. Why do I still have my mask on? It's because I was teaching people in person and were required to wear masks. So I don't need that while I'm in here since you're over a camera. I don't know what I'm doing. Anyway. So that is all that we are saying with these infinite limits. Now, if you want to do the one-sided limit, then again, you just restrict yourself to x smaller than a or x bigger than a, depending upon whether we're coming in from the left or whether we're coming in from the right. So I'm not going to rewrite this entire thing. Now, how do you figure out whether something is blowing up positively or negatively? Well, normally you just kind of figure out what is going on with the sign of the thing near that point, okay? So like if I want to analyze the limit as x approaches 0 from the left of 1 over x versus limit as x approaches 0 from the right of 1 over x, and the limit as x approaches 0 of 1 over x, well, for x smaller than 0, 1 over x is negative, so this must be blowing up to negative infinity. Because I do have a vertical asymptote here, it is blowing up, but it's negative. So it blows up negatively, negative infinity. On the right-hand side, we are positive, so we must be blowing up to positive infinity. This limit does not exist. It doesn't really not exist. It is completely undefined because since it's blowing up to negative infinity on the left and positive infinity on the right, it's not really doing just one thing, and therefore, even as an infinite limit, the two-sided limit does not exist. More generally, when you're dealing with these kinds of problems, you want to kind of think back to what you did in pre-calculus when you were dealing with vertical asymptotes. So if you remember, when you talked about a vertical asymptote, you had to figure out, well, does the function approach the vertical asymptote going up, or does it approach it going down? Well, these infinite limits are really just that same kind of thing. So if I want to do something like p of x over q of x, the limit as x approaches a of p of x over q of x from the right or the left, and let's suppose that q of a is equal to 0 here, but p of a is not equal to 0, well, in this case, we're going to get a vertical asymptote. And in order to decide whether I approach that vertical asymptote going up or going down, I just need to figure out where is p of x over q of x bigger than 0 and where is it less than 0. If it's bigger than 0 as I approach a, then it must be blowing up to positive infinity. If it is less than 0 as I approach a, it must be blowing up towards negative infinity. So let's just give a quick example of this kind of thing. Let's suppose that I have the limit as x approaches 1 of x squared, let's say, minus 4x plus 3, or actually let's do as x approaches negative 1, and then this is divided by x plus 1. And we will do the left-hand limits, and then we'll see what that says about the actual limit itself. So what I want to do is I want to check, now at negative 1, the bottom is going to be 0, but the top is not. In fact, what I can say is x squared minus 4x plus 3 over x plus 1. This is equal to x minus 3 times x minus 1 divided by x plus 1. So it is going to have a non-zero over 0 going on here when I plug in x equals negative 1. So then the question is, where is this function positive and where is it negative? Well, remember, a rational function can only change signs when the numerator or the denominator have roots. So this is going to change signs at x equals minus 1, x equals positive 1, and x equals 3. Those are the only places that this thing is allowed to change signs. And then I just need to figure out where is this thing positive and where is this thing negative. One way that I like to do that is I mark off -1, +1, and 3 on a number line, and then I think about points on the number line. So like at x equals 0, I would have -3 times -1, that's +3, divided by 1, that would be positive, so at 0, this thing is positive. Now, when does it change signs? Well, it changes signs if the root has odd multiplicity. All of these have odd multiplicity, so this thing does change signs at each of these roots. Remember, the multiplicity is just the exponent on that particular factor. So in this case, they all have multiplicity 1. And that means that as I come in towards x equals -1 from the left, x squared minus 4x plus 3 over x plus 1. Well, as I come in from the left, this is going to be negative infinity because I'm negative. I have to go down towards negative infinity. Limit as x approaches -1 from the right of x squared minus 4x plus 3 over x plus 1. Here, the function is positive, so it must be going towards positive infinity. The limit as a whole, therefore, is undefined because it's not blowing up in just one direction or the other. Now, these limits are important, though, in terms of the way the graph is going to look, because it means when I make my graph at -1, I have a vertical asymptote, and I go down on the left, but up on the right-hand side near that vertical asymptote. Let's take a look at one more example of the sort of thing that we have here. So let's look at the left, right, two-sided limits at x equals 2 for, let's suppose that I have x minus 3 divided by x plus 2 squared. Okay, so first of all, whenever you're dealing with a limit, you first want to just see if you can do it by evaluation, if you're dealing with a rational function. I'm sorry, I meant to say x minus 2, not x plus 2. Excuse me. In this case, we cannot just do it by evaluation because we get -1 over 0. That tells me that we're going to get some kind of a vertical asymptote. So let's think about where this thing is positive and negative. The sign changes for this rational function are going to be at x equals 2 and x equals 3 possibly. But x equals 2 is going to have a multiplicity of 2. So that one is not going to be a sign change. The only change in sign is going to happen at x equals 3. And so then I just need to figure out, is this thing positive or negative at, one point over here. Again, if I pick, let's say, x equals 0, -3 over -2 squared, it's going to be negative there, so it's positive over here on the right. Now, at -2, what we're going to get is a vertical asymptote, but it's still negative on both sides because that asymptote corresponds to a root of multiplicity 2. So that means that the left-hand limit and the right-hand limit are going to be negative infinity. So we can say the limit as x approaches -2 from the left, x minus 3 over x minus 2 squared, is negative infinity. And that is also the limit as x approaches -2 from the right. And that means, because it's blowing up in the same direction on both sides, we can say that the limit as x approaches -2, x minus 3 over x minus 2 squared, is equal to negative infinity. So because it does the same thing on both sides, and that's important, we can say that this is negative infinity. So there are two examples of working out infinite limits. Now, one more thing that I want to observe about infinite limits is the following fact, which will become useful later on. So notice, and this is maybe a sort of straightforward observation, but it becomes important later on. So we may as well make this observation now. If the limit as x approaches a of f of x is equal to plus or minus infinity, this implies that the limit as x approaches a of the reciprocal of f of x is equal to 0. Okay? And the other direction is sort of almost true. What is true is that if the limit as f of x approaches 0, as x approaches a of f of x is equal to 0, then the left and right limits of its reciprocal are plus or minus infinity. What it doesn't imply is that the actual limit exists, and the reason is because the left and the right limits could be different. So this direction, if the limit is infinite, the limit of the reciprocal is always 0. But if the limit is 0, then we only know that the left and the right hand limits of the reciprocal are plus or minus infinity. They don't have to be the same thing. So for instance, limit as x approaches 0 of x is equal to 0. Limit as x approaches 0 from the left of 1 over x is negative infinity, but limit as x approaches 0 from the right of 1 over x is equal to positive infinity. So there are these two kind of totally separate things here going on. Well, not totally separate. They're related, but the point is the limit itself for 1 over x doesn't exist. The best we can say then is that the limits of these reciprocals on the left and the right will be plus or minus infinity, but they may not necessarily be the same thing, okay? So it's not like you get a full converse to this. Why is this important? Well, because later on we're going to deal with other ways of handling fractional or limits of fractions where the numerator and the denominator both blow up. And it's nice sometimes to be able to switch things around and work with their reciprocals and things like that, just depending upon what we want to do. Okay. There's my eraser. I lost it for a moment. So let's now talk about limits at infinity. Limits at infinity refer essentially to horizontal asymptotes. So whereas the vertical asymptote refers to the infinite limits refer to the vertical asymptotes, the limits at infinity refer to the horizontal asymptotes. So if I have something that does this kind of thing in a graph, let's say that it goes off like this, and this is my y equals f of x, then what I want to write is the limit as x approaches infinity of f of x is equal to L. And we will call that a limit at infinity. And maybe on the other side, maybe it does something different. Maybe on the left-hand side, it does something like this. And it still approaches an asymptote, but it's y equals k. In this case, I want to say the limit as x approaches negative infinity, f of x is equal to k. And it can cross these limits, like maybe it starts fluctuating back and forth. But the point is, it gets closer and closer to that horizontal line as we keep going out along the graph. Well, that is a limit at infinity. Now again, infinity is not a real number. So it doesn't correspond to some point along the graph. We're not saying it takes on some value. It doesn't have to ever achieve this value. What we are saying is that if you kept on going out to the right, you would find that this curve gets closer and closer to this horizontal line. If I keep on going out to the left, you'll find that the function gets closer and closer on both sides here. Now, how do we phrase that precisely? Well, it turns out it's not super difficult to do if we think back to what we've done before, but again, it is a rather technical thing to write out. So we will say that the limit as x approaches infinity of f of x equals L. This means that for any epsilon bigger than 0, there is a value m such that when x is bigger than m, the absolute value of f of x minus L is less than epsilon. So what does this mean? Well, it means here's my y equals L. Here's y equals L plus epsilon and y equals L minus epsilon. If I have some picture of my function here, it means that past m, my function is sandwiched in between L minus epsilon and L plus epsilon. And as skinny as I want to make this strip, no matter how much I want to shrink this strip down, I can always guarantee the function will be sandwiched in between these two things, provided that, I pick my m to be far enough out to the right. So as long as we go far enough to the right, we can guarantee the function is inside of this strip. Same kind of deal happens if we're talking about limits towards negative infinity, except we're going to take this picture and turn it around. So we will say that the limit as x approaches negative infinity of f of x is equal to L if, for any epsilon bigger than 0, there is an m such that when x is less than m, the absolute value of f of x minus L is less than epsilon. So it's literally the same picture, except now, instead of going off to the right, I'm saying I would be sandwiched in between these two. I will be sandwiched inside this strip, provided that I go to the left of some vertical line here. As long as I am to the left of this m, I will be sandwiched inside of this strip. And that is going to be a limit as we approach negative infinity. Now, how do you calculate these things? Well, calculating them in general can be somewhat tricky, depending upon what your function is. But for rational functions, we already kind of know the answer. So that's because we know how to find horizontal asymptotes. So for p of x over q of x, rational functions the limits are the horizontal asymptotes. I mean, in general, limits at infinity give you horizontal asymptotes. So that's nothing special. But what is special is that I know how to calculate these from the stuff we've talked about in pre-calculus. And how do we do that? Well, what you do is you take your two functions and you multiply on the top and the bottom by the largest power of x that shows up, and then you ask yourself whether that comes out to be a finite number. So if I want to do the limit as x approaches infinity of, let's say, 3x squared minus 2x plus 1 over 5x cubed plus 2x squared, what I do is the highest power of x here is an x cubed. So I multiply everything by 1 over x cubed. This is going to be the limit as x goes to infinity of 3 over x minus 2 over x squared plus 1 over x cubed divided by 5 plus 2 over x. And all of these are going to go to 0 because as x gets very large, these get very, very small, except for this 5 in the denominator. So this limit is going to be 0. And there we go. That's all that we can say about this. I really need a better pen. So excuse me for 1 second while I figure out what I did with my bag. Here is the bag. The box of pens is inside the bag. Hopefully this pen will work. Sorry, I'm waiting for information from my wife because our dog is actually getting spayed right now. So I was just checking to make sure she wasn't updating me on that. Okay, now another example of this kind of thing. What if I want to do the limit as x approaches negative infinity of, let's say, 4x squared plus 3x minus 1 divided by negative 2x squared plus 5x plus 2. The largest power here is the x squared. So let me multiply on the top and the bottom by x squared. And when I do that, you can see this x squared is going to cancel. This is going to become over x. And these are going to become over x squared. Whoops, I don't want to actually cancel that. And then all of these are going to go to 0 except for these first two. So this is going to be the limit as x approaches minus infinity of 4 over negative 2. And that's just going to be negative 2, because 4 divided by negative 2 would be negative 2. And the limit as we approach infinity of some constant is still just that constant. So this comes out to be minus 2. And there we go. Now there are some other functions that don't necessarily have limits at infinity. So for instance, if I were to try to do, let's say, the limit as x approaches infinity of cosine x, well, this does not exist. And the reason it doesn't exist is because cosine of x, this keeps on fluctuating between positive 1 and minus 1 forever. That's probably the worst drawing of cosine x anybody's ever made. But you can see the idea here, and you can see it just keeps on fluctuating forever. It never settles down towards one particular value. Therefore, this limit doesn't exist in any sense. It's not going to be any kind of limit that we can talk about. Same would go if I talked about, say, the limits at infinity of sine of x or something like that. Or even tangent x. Tangent x is really bouncing all over the place because tangent x, that is the one that has the vertical asymptotes like so as we keep on going out here. It really is all over the place. It never settles down towards one particular horizontal asymptote. But there are some situations in which we can say, actually, there's an infinite limit at infinity. And infinite limits at infinity, or negative infinity, this just means that as we go off towards one side, the function is going up without ever stopping or going down without ever stopping. So as an example of this, if I do the limit as x approaches infinity of negative 2x squared minus 1, well, as x gets bigger and bigger, this continues to get more and more negative, and so this is going to be negative infinity. On the other hand, if I do something like the limit as x approaches minus infinity of, let's say, negative 3x cubed plus 4x, in this case, as I plug in larger and larger negative numbers, x cubed is a very big negative number, it's multiplied by a negative, well, this comes out to be positive infinity. And when you're dealing with polynomials, the only thing that matters for these limits at infinity being infinity or negative infinity, the only thing that matters is going to be the highest degree term. The other terms don't really matter. The reason for that is if I take a big number and I cube it, that is much larger than what happens if I just take the number by itself, or even the number squared, right? Like if I have 1,000 squared is 1,000,000, that's big, but 1,000 cubed is 1,000,000,000, which is much bigger than 1,000,000. So as you go off towards the edges, eventually the only term that really matters in terms of whether we're going up or down is going to be that first term. The same sorts of things apply to rational functions as we go off towards infinity. All that really is going to end up mattering is what happens with your first terms. So let's think about why that is the case. Let's suppose that I want to do the limit as x approaches minus infinity of, let's say, 5x cubed minus 3x squared divided by 2x squared plus 4. Well, what's going to happen is I can multiply everything. I don't want to actually multiply by the largest term here. I want to do the largest term in the denominator. I think I just did the largest term before, but usually you just want to do the one in the denominator. If I multiply everything by 1 over x squared, what I'm going to get here is the limit as x approaches negative infinity. Then I'm going to have 5x minus 3 divided by 2 plus 4 over x squared. And we can pretty much ignore the 4 over x squared and just think about this part here. Because this part is going to start to get smaller and smaller and smaller. We can basically ignore it. It changes it changes the value, but it changes it by such a small amount that we can just disregard. Now, what am I left with? Well, this part here that I've put in this funky little circle thing, this is really just a polynomial because this is 5 halves x minus 3 halves. Okay, that's a polynomial, but the only thing that determines whether this is approaching positive or negative infinity is going to be the first term, which is 5x over 2. Well, as x becomes a very large negative number, multiplying by 5 halves gives me a very large number, so this becomes minus infinity. And this same procedure will work no matter what these polynomials are in my rational expression. You just, ultimately, when you multiply like this, you can end up just analyzing the first two, like the first term over the first term, and seeing what happens to that. That will tell you your limits at infinity. It'll even tell you whether they are positive or negative infinity. Now, you do have to be careful if you're talking about oblique asymptotes or something. It's not quite this simple. If you want to do oblique asymptotes, then you have to do full-on polynomial division and find the quotient and the remainder, and then it's actually going to be the quotient that ends up mattering in terms of oblique asymptotes. But fortunately, in terms of limits, this is actually simpler than doing oblique asymptotes and things like that because we don't care. We just care whether this thing is going to positive or negative infinity or if it's approaching some particular value. It's all we care about. One more thing that I want to notice here is there are other examples of functions whose behavior towards infinities we understand. For instance, if I take the limit as x approaches minus infinity of e to the x, well, what does e to the x look like? It looks like this. As I go off towards the left here, I approach a horizontal asymptote of 0. And so this limit, as x goes towards negative infinity, will be 0. As I go off towards the right, this is growing and growing and growing, so this is going to be an infinite limit at infinity. So this just expresses the fact that the exponential function blows up. Now you might wonder, what would happen if I wanted to look at the limit as x goes to infinity of two things that are both blowing up, but maybe it's not just a nice rational expression. Like, what if I have e to the x divided by x? Well, that's a tricky question. It's a tricky question because these are blowing up, but this isn't a rational function. I can't just deal with it the way that I did with the rational expressions. It turns out there is a way to see what is going on with this kind of thing, but unfortunately, it's going to have to wait for the moment. We don't yet have the tools to answer this kind of question. But I would encourage you, if you're interested in this, try graphing this and see what it looks like. See if you can kind of figure out sort of what it looks like it's doing and kind of guess what the answer should be. But like I said, to precisely give an answer to this is going to be kind of a lot of work. It may not be too difficult to sort of guess what's going on here. Because the thing is, we know exponential functions, they get very big very fast. Like, this function is growing and growing and growing and growing and growing. X grows, but it grows at sort of this constant rate. It doesn't just keep on growing faster and faster. So you might expect that this still blows up towards infinity. If that's what you guess, that is correct. But we'll have to see later how you actually prove that. Now, I encourage you, take a few minutes to sort of think about some other functions that you know. Maybe some functions like arctangent. Think about those limits at infinity. What are the limits for that function? Think about the infinite limits that you get with functions like tangent of x. Look at the vertical asymptotes and think about how you would phrase the behavior at the vertical asymptotes in terms of limits. If you can do that kind of thing, it will show that you really understand your limits. So that leads us into the classic joke in mathematics, which sort of makes more sense in another context of limits, but in which an infinite collection of mathematicians go into a bar, and the first one orders 1 pint of beer, the second one orders half a pint, the third one orders a quarter pint, the fourth one orders an eighth of a pint, and so on, and the bartender just hands them 2 pints and says, "Know your limits." That makes more sense, perhaps, in a Calc 2 context. Anyway, we're going to end there today with that really awful joke. I apologize. And we will pick back up on talking about some more stuff in the next lecture.